Have you ever thought about the scary photos Voyager 1 might take after 100 billion years in space? Because let me tell you, even after just 47 years drifting in the dark cosmic clouds, Voyager 1 has already sent NASA some unbelievable pics. And those revelations have changed the reality for us. Like you might know, Saturn has rings and Jupiter is huge. But Voyager 1's images reveal that's just a tiny fraction, and there's a lot more to discover. But the question arises, can a human-made object really last 100 billion years in space? And how far has this spacecraft traveled till now? We're going over its possible encounters with black holes traveling through interstellar space, coming across galactic collisions and supernova remnants. So you might be wondering why this tiny spacecraft is out there snapping scary pictures of the universe and how freaky it can get after 100 billion years. Let me fill you in on a bit of the backstory about Voyager 1, our brave little space explorer that was launched way back in 1977. Originally, it was meant to check out the outer planets. It was supposed to study Jupiter and Saturn up close, giving us some mind-blowing images and data that totally changed what we knew about these giant planets and their moons. And surprisingly, things got a lot more spine-chilling as time went on. And do you know that Voyager 1, since its launch in 1977, has already traveled an incredible distance? But let's stretch our imaginations a bit further. What if Voyager 1 kept going for 100 billion years? Yep, you heard me right, 100 billion years. That's more than 7 times the age of the entire universe, which is about 13.8 billion years old. Imagine all the cosmic events from the birth of the first stars to the formation of galaxies and our solar system, and then multiply that by 7. That's the kind of timescale we're talking about. Voyager 1 is zooming through space at around 17 kilometers per second, which translates to roughly 61,200 kilometers per hour. Over the span of 100 billion years, this little spacecraft would cover an unfathomable distance. For some perspective, a light year is about 9.46 trillion kilometers. At its current speed, Voyager 1 travels around 1.3 light years every 75,000 years. So, in 100 billion years, it would cover roughly 1.3 million light years, taking it way beyond the Milky Way galaxy into the vast empty stretches of intergalactic space. Picture the universe in 5 billion years. Our sun will have used up its fuel, expanded into a red giant, and eventually shed its outer layers, leaving behind a white dwarf. Earth, Mars, and the gas giants will either be engulfed or scorched by the sun's fiery expansion. But Voyager 1? It'll be far from these cosmic fireworks, drifting silently through the cold emptiness of space, totally unbothered. Fast forward to 100 billion years, and the universe will be a very different place. Stars will be a rare sight. The rate of star formation is slowing down, and will eventually enter an era dominated by dim red dwarf stars that burn their fuel so slowly they can last for trillions of years. By then, many of the stars we know, including our sun, will have long died out, leaving behind white dwarfs, neutron stars, and black holes. But what happens if Voyager 1 gets close to a black hole during its 100 billion years journey? Well, as we know, black holes are like the universe's ultimate vacuum cleaners, where gravity is so strong that nothing, not even light, can escape. If Voyager 1 were to pass near one, it would experience gravitational lensing. This is where the black hole's gravity bends and warps the light around it, creating some trippy visual effects. Imagine looking through a funhouse mirror, but on a cosmic scale. Light gets twisted into rings and arcs, known as Einstein rings, making the whole scene look like something out of a sci-fi movie. For instance, there's the Einstein cross, a quasar about 8 billion light years away. Its light gets bent by a foreground galaxy to form multiple images. Voyager 1 might not capture something exactly like that, but if it passes near a black hole, we could see some similarly bizarre and surreal scenes. The gravitational pull would create visual distortions that make you question everything you know about space and light. And then there's the radiation. Still, black holes aren't just gravitational monsters, and they will not even after 100 billion years. The accretion disk, a swirling mass of gas and dust around the black hole, emits intense X-rays and gamma rays. If Voyager 1's instruments could handle the radiation, it might capture images of this bright, chaotic disk. The event horizon, the point of no return for anything getting too close to the black hole, would appear as a dark void surrounded by the luminous, frenetic accretion disk. It's like the ultimate cosmic light show, but way scarier. Now let's talk about neutron stars and Voyager 1 meeting up after 100 billion years. These are the remnants of massive stars that went supernova. They're incredibly dense and have magnetic fields billions of times stronger than Earth's. If Voyager 1 gets near a neutron star, its magnetic field could mess with the spacecraft's instruments, possibly creating some weird data. One of the coolest types of neutron stars is a pulsar, which emits beams of radiation from its magnetic poles. As the star rotates, these beams sweep across space, kind of like a cosmic lighthouse. Take the Crab pulsar, for example. After 100 billion years, it will be in the center of the Crab Nebula and spin 30 times per second, sending out regular pulses of radiation that we can detect from Earth. If Voyager 1 encounters a pulsar, it might capture images and data of these beams, appearing as periodic flashes or arcs of light against the dark backdrop of space. These beams of radiation from pulsars aren't just scientifically fascinating, they're visually stunning too. Voyager 1 could record these eerie, rhythmic pulses of light, showing how they illuminate the surrounding space in a hypnotic pattern. The interaction of these beams with any nearby gas or dust could create even more visual phenomena, like glowing arcs or brightened regions, adding to the spooky beauty of the scene. The area around neutron stars and pulsars is full of high-energy particles and strong gravitational fields, which can produce more visual and data anomalies. Voyager 1 might record sudden bursts of radiation or capture intricate details of the neutron star's surface. Imagine seeing a crust of superdense material, and maybe even starquakes, movements in the crust caused by the intense gravitational forces. Back in 1967, Jocelyn Bell Burnell and Anthony Hewish discovered the first pulsar, shaking up our understanding of neutron stars and stellar evolution. If Voyager 1 could capture close-up images of such objects, it would be a fantastic continuation of that legacy, adding to our knowledge of these cosmic phenomena. Now let's talk about the connection of dark matter and rogue planets with Voyager 1 after 100 billion years. That's the kind of stuff that keeps astrophysicists awake at night. Dark matter is like the universe's invisible glue, making up about 27% of everything out there. It doesn't emit, absorb, or reflect light, so you can't see it with any telescope. Its presence is known only because of the gravitational effects it has on visible matter, like galaxies and galaxy clusters. Imagine this. Dark matter acts like a cosmic scaffolding that holds galaxies together. Back in 1933, Swiss astronomer Fritz Zwicky proposed the existence of dark matter to explain why galaxies weren't flying apart, considering the missing mass in galaxy clusters. Even after tons of research, we still haven't directly observed dark matter. But if Voyager 1 were to pass through a dense patch of it, its instruments might pick up subtle gravitational influences, like unexpected changes in its speed or direction. Now, trying to visualize dark matter is a tricky business since it's invisible, but let's play around with some ideas of 100 billion years. If Voyager 1 flew through a dark matter-rich area, we might see gravitational lensing in pictures that it will take where light from distant stars or galaxies bends around the dark matter. This could create some seriously bizarre and distorted images, like cosmic funhouse mirrors. Think of it as seeing light twisted into arcs and rings, similar to what we've observed around massive galaxy clusters. In places where dark matter interacts with normal matter, we might see some unique gravitational phenomena. For example, if dark matter particles bump into each other, they could produce faint gamma ray emissions. Voyager 1's instruments might detect these as subtle flickers, or bursts of light against the dark expanse of space, giving us a tantalizing glimpse into this mysterious substance. Then there are rogue planets, the loners of the cosmos. And believe me, they will be real fun after 100 billion years. These planetary mass objects drift through space without being tied to any star. They're thought to be either ejected from their original star systems or formed in isolation. The Milky Way might be teeming with billions of these wandering planets, but they're nearly impossible to see because they aren't illuminated by starlight. The first potential rogue planet PSOJ 318. 522 was discovered in 2013, about 80 light-years away. It's roughly 12 times the mass of Jupiter. Detecting rogue planets usually involves spotting their faint infrared emissions from residual heat. If Voyager 1 stumbles upon a rogue planet after so many years, it could take some of the shocking and most unique images ever captured. These planets would appear as dark silhouettes against the starry backdrop of space. With its infrared sensors, Voyager 1 could detect the faint heat signatures of these planets, revealing their shapes and surface features. Imagine seeing a rogue planet's cold, barren surface, with temperatures plunging to near absolute zero. But if it has some internal heat source, like radioactive decay or residual heat from its formation, we might see geothermal activity. Picture glowing volcanic vents casting an eerie light on an otherwise pitch-black landscape. Some rogue planets might have thick atmospheres, showing off weather phenomena like storms and auroras driven by internal heat. Voyager 1 could capture dramatic visuals of swirling clouds and flickering lights illuminating the dark surface, offering unprecedented insights into these isolated worlds. As Voyager 1 travels through interstellar space, it's not just empty void it's exploring. This vast region is sprinkled with sparse particles of gas and dust, cosmic rays, and of course, dark matter. In 2012, Voyager 1 crossed the heliopause, the boundary where our sun's solar wind gives way to the interstellar medium, and officially entered interstellar space. Its instruments detected a rise in cosmic rays, marking its entry into this new frontier. Voyager 1's ongoing journey will provide invaluable data on the interstellar medium's composition and properties. By studying the interactions between cosmic rays, interstellar particles, and dark matter, scientists can gain deeper insights into the fundamental processes shaping our galaxy and the universe beyond. And it's impossible to talk about space and Voyager 1 travel after 100 billion years without exploring the epic drama of galactic collisions. These cosmic smash-ups are like the ultimate space reality show, with galaxies crashing into each other, creating some of the most jaw-dropping scenes in the universe. If Voyager 1 managed to snap some pics of a galactic collision, we'd get a front-row seat to these celestial brawls. So what goes down during one of these galactic meet and greets? When two or more galaxies get too close, their mutual gravitational attraction pulls them together, creating a cosmic dance that can last millions to billions of years. Eventually, these galaxies might merge into one giant galaxy. Imagine the Milky Way hooking up with the Andromeda Galaxy, which is set to happen in about 4.5 billion years. Now that's a future blockbuster. The images of galactic collisions after 100 billion years will be pure chaos and beauty. Stars, gas, and dust get tossed around like confetti, forming intricate, twisting shapes, tidal tails, and bridges. These structures stretch across vast distances, making the whole scene look like a cosmic ballet. Just look at the antennae galaxies, NGC 4038 and NGC 4039, located about 45 million light-years from Earth. These two are in the middle of a spectacular collision, with long, sweeping tails of stars and gas captured beautifully by the Hubble Space Telescope. As Voyager 1 roams the cosmos, it might stumble upon similar scenes of galactic collisions. The images it captures would show the intricate dance of stars and gas, with bright knots of new star formation lighting up the cosmic stage. These snapshots would offer invaluable insights into the dynamics of galaxy interactions and the processes driving the evolution of galaxies. And when galaxies finally merge, the real fireworks begin. Galactic mergers are the grand finale of these cosmic interactions. When galaxies merge, their central black holes can also collide, releasing enormous amounts of energy and creating powerful gravitational waves. This merging process often triggers intense bursts of star formation, known as starbursts. Gas and dust in the galaxies get compressed and heated, sparking the birth of thousands of new stars, lighting up the merged galaxy like a cosmic firework display. One of the most famous examples of a galaxy merger is the Whirlpool Galaxy, M51, and its companion, NGC 5195. Located about 23 million light-years from Earth, the Whirlpool Galaxy is in the process of merging with its smaller companion. This interaction has triggered waves of star formation in the Whirlpool Galaxy's spiral arms, creating bright blue clusters of new stars. Images of this merger, captured by the Hubble Space Telescope, show the detailed structure of the spiral arms and the bright knots of star formation. Voyager 1, with its ability to capture images from distant regions of space, could potentially observe similar galactic mergers. The images would show the dramatic and chaotic process of two galaxies merging, with streams of stars and gas intertwining and new stars being born in brilliant bursts of light. These observations would help astronomers understand the role of mergers in the formation and evolution of galaxies, as well as the conditions that lead to intense periods of star formation. And let's not forget the aftermath of stellar explosions called supernova remnants, captured after 100 billion years. These colorful and dramatic remains of massive stars that have gone supernova will be like nature's own fireworks. When a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core collapses, releasing an enormous amount of energy and ejecting the outer layers into space. This results in beautiful, intricate structures in the surrounding gas and dust. Take the Crab Nebula, Messier 1, for example. Located about 6,500 light-years from Earth in the constellation Taurus, it's the remnant of a supernova observed by Chinese astronomers in 1054 AD. Images captured by telescopes like Hubble show a complex and colorful structure, with filaments of gas and dust glowing in various wavelengths of light. The central region contains a pulsar, the rapidly spinning neutron star left behind by the supernova. If Voyager 1 were to photograph a supernova remnant, the images would likely show similar structures, with bright filaments of gas and dust illuminated by shock waves from the explosion. The colors and shapes of these filaments would provide clues about the composition and dynamics of the ejected material, as well as the nature of the progenitor star. Such images would be invaluable for studying the life cycles of stars and the processes that drive the enrichment of the interstellar medium with heavy elements. Another notable supernova remnant is Cassiopeia A, CA's A, located about 11,000 light-years from Earth in the constellation Cassiopeia. CA's A is the remnant of a supernova that occurred around 16,080 AD, and its images reveal a complex shell of glowing gas and dust. The remnant is expanding at a rate of about 4,000 to 6,000 kilometers per second, and the detailed structures within the shell provide insights into the explosion dynamics and the interaction of the shockwaves with the surrounding medium. Voyager 1, although not equipped with the same high-resolution imaging capabilities as modern telescopes, could still capture valuable images of these cosmic phenomena from unique vantage points in space. The data obtained from such observations would complement the findings from ground-based and space-based telescopes, providing a more comprehensive understanding of the violent and beautiful events that shape our universe. Voyager 1 has snapped some of the most mind-blowing images ever seen, showing us a universe wilder than we ever imagined. But let me ask you this. Don't you think it's downright hilarious to think we've seen it all? The universe is full of surprises, and who knows what other cosmic wonders are out there just waiting to be discovered. Touch the subscribe button, or whatever.